So let me begin by thanking the organizers. It's always a great pleasure to be here, and I'm really happy to have this opportunity once more. So what I want to talk about today are some ideas that we've been working on. And what we're trying to do is to see if basically we could reduce sampling rates, even in applications where we don't have structure on the input. So what I want to show you today are some examples in this direction, and hopefully this will inspire more work in this general direction. So, of course, traditional sampling theories talk about at what rate we need to sample an input signal, x of t, when our goal is to recover the signal itself. And there's many well-known results, of course, the well-known Shannon-Nyquist theorem that talks about band-limited signals, its extension, the Landau rate, which talks about multiband signals, so signals that have several bands of information where we know their location, we know the spectral support. And in this case, the minimal sampling rate is just what's called the Landau rate, the actual band occupancy. And both of these are special cases of what's called subspace sampling, where basically the sampling rate that we need are the degrees of freedom in the subspace. Okay, so this is kind of traditional sampling theory. Now, more recently, and particularly in the past decade or so, there's been a tremendous amount of work on exploiting structure in order to reduce sampling rates. Okay, so there's many, many examples. These are just a subset. So we've worked, for example, on the multiband model, and others have worked on this problem as well, where it's the same as the Landau problem, but we don't know the carrier frequencies, or we don't know the spectral support. And in this case, the price to pay is a factor of 2, so the minimal sampling rate is twice the Landau rate. There's, for example, the beautiful framework of finite rate of innovation, who's inspired by Vetterli and a lot of his colleagues. And one particular case that they've looked at many cases, but one special case is this pulse tree model, where we have, for example, k pulses. And in this case, the minimal sampling rate is 2k, again, which could be much lower than the Nyquist rate. And more generally, we could look at these union of subspaces models, where we have many possible subspaces. Only one of them is the correct one. Both of these problems, the multiband model and this pulse tree model, are special cases of the union model. And in this case, the minimal sampling rate is the rate associated with the sum of two spaces, even if we have many, many spaces. So again, a reduction with respect to the Nyquist rate. Now, of course, in the discrete setting, we have the famous sparse vector case, which is the basis behind compressed sensing. And we all know that if we have a sparse vector, we could recover it from a small number of measurements. So these are all cases where basically we exploit the structure on the input signal in order to reduce sampling rates. Now, there's also been a lot of activity in actually building hardware to achieve these low-rate samples. So not only theory, but actually hardware that goes with it. And particularly in our lab, we've been focusing on this quite a bit. So what you see over here are just some examples that we've developed in our lab for a variety of different applications. And of course, there's many other people who have been working on this as well. And the goal here is to show that these ideas can actually be useful in practice to reduce sampling rate. Now, of course, the difficulty is that we don't always have structure on the input. So these are particular cases where there is structure, but there's many examples when the signals are arbitrary. And what we were concerned with is whether the hardware that we built, we worked so hard to build it, could we still apply it even in cases where there is no structure? And what I want to show you now are some examples of when this is possible. Of course, in general, this can't be done, but in special cases, it can. And what are these cases? Well, we're going to look at cases where we're not actually interested in recovering the underlying signal x itself, but we're interested in some function of the signal. Okay, so to make this more concrete, we're going to look at three particular examples. There's other examples along similar lines. So the first case is when we're not interested in recovering the signal, but we're actually interested in recovering the power spectrum. And there's many applications of this. We'll show that later on. The other example is when we are interested in recovering the signal, but we take quantization into account. So unfortunately, we're not given samples directly of the signal, but these samples are quantized. And this is quite interesting. What we'll show in this case is that because there's distortion introduced by the quantization, we could actually sample at rates that are much lower than the Nyquist rate and still achieve the optimal rate distortion curve. So essentially, because there's distortion anyway, we don't lose anything by sampling at sub-Nyquist rates, even when there's no structure on the input. Okay, and the last application we're going to look at is when we have multiple signals, multiple correlated signals. And the particular example we're going to focus on is ultrasound, but the same type of problem arises, for example, in radar and many other applications. And in this case, what we want is not to recover the individual signals, but actually to recover a processed version of these underlying correlated signals. And particularly, we're going to focus on the process of beamforming, which is basically just an alignment and summation of these signals. So we'll see that in this case, because we only want the processed version, again, even though these individual signals don't have structure, we could exploit the processing task and reduce the sampling rates. Okay, so this is what we're going to be talking about today. Here's a specific outline. We're going to start with power spectrum estimation. We'll then talk about, very briefly, about what we call rate rate distortion theory of analog signals. Okay, so we're going to characterize the rate distortion of continuous time inputs and see that the rate distortion curves that we get actually allow subsampling even with arbitrary inputs. And finally, we're going to talk a little bit about ultrasound, so I'll give you some background to this application, and we'll see how we could reduce sampling rates in ultrasound even though the individual signals don't have structure, because we're exploiting the processing task of beamforming. Okay, and this we'll talk about a little bit because I think it's a cool application. I'll show you a neat demo of this. And the main thing that we're working on in the context of ultrasound are actually two applications. One is wireless ultrasound, and I'll show you a demo of that. So because we could reduce the sampling rates, we can actually allow a wireless probe where we take the image at one side of the room, and then because the rate is reduced, we can actually send the data over a standard wireless link, and then you could recover your image either over the cloud or at some other remote location. And this is of great interest to clinicians, and we're actually working now on commercializing this idea. The other application of these ultrasound ideas is to 3D ultrasound, where the volume of data is huge. So reducing the sampling rate actually enables increased resolution, which is very important in cardiac imaging. So that's another application we're working on. Okay, so let me begin with power spectrum estimation. There's many applications where we sample the signal, but we're not actually interested in the signal. We're interested in recovering its second-order statistics. So specifically, our work was motivated by cognitive radio, where we want to locate the occupancy of the signal. We want to know where the signal is coming from, but we're not interested in the signal itself, just knowing its band location. And in this case, of course, the band location of the signal is the same as the band location of the power spectrum, but the power spectrum is more robust to noise. So estimating the power spectrum is actually more efficient, not only in terms of sampling rate, but in terms of statistical robustness, than estimating the signal. There's many other applications in signal processing where the parameters that we're interested in are actually embedded in the second-order statistics, in the covariance. Okay, so array processing is a particular example where we typically estimate our parameters, like the direction of arrival, from the covariance. So we never really care about the signal itself, but only about its second-order statistics. So in these cases, the question is, what is the minimal sampling rate needed when we sample a signal, but we only want to estimate its covariance? And what we're going to see is that actually it could be surprisingly low, okay, particularly for ergodic stationary signals that we're going to be focusing on. So just to make the problem more specific mathematically, so we're assuming that we're going to sample our wide-band stationary ergodic signal with a stable sampling set. So the sampling is stable for x of t. And our goal is to recover the correlation, or the power spectrum. Of course, it's the same. So what's the intuition, before I give you the result? Why do we think that we could reduce the sampling rate? Well, actually, the intuition is quite simple. So when we sample, okay, we're looking at the individual points. So here's our sampling set, which has a very low density. Okay, so from this density, we can't recover, for example, a band-limited input. But when we're estimating the covariance, we're actually looking at the differences, okay, because it's a stationary process. So we're interested of the differences in the sampling set. And if you look at the sampling set and look at all possible differences, you see that the difference set actually has many, many points. So the density of the difference set is quite large. And therefore, from the density set, we can, in fact, estimate the covariance. Okay, so this is just to give some intuition to why this is possible. Now, this is, of course, an old problem. So there's early papers that looked at this, particularly in the context of random sampling. And it was shown already in the 70s that if we use random Poisson sampling, then as long as the average sampling rate is greater than 0, we could get a consistent estimate of the power spectrum. Okay, but we're interested in deterministic sampling. Okay, we're looking, like I showed at the beginning, we're looking at specific hardware that does deterministic sampling. And in recent years, there's been more look at this, again, along these lines of sub-Nyquist sampling. So there's been several different results that looked at, for example, multi-coset sampling or coprime sampling. And they looked at specific constructions where the density goes to 0 and showed that recovery is still possible. So there's been these specific results in the literature. And basically, what we want is to develop a general framework. So given a sampling set, we want to be able to determine whether we can estimate the covariance from it or not, kind of equivalent to what we have for band-limited sampling. So the main result that we can show, the first main result that we can show, is that we could construct sets that have a Bernoulli density, basically an average density of 0. Okay, so the sampling rate is essentially 0, but the Bernoulli density of the difference goes to infinity. And this will mean that we could recover the covariance from this density set. Okay, so in order to be able to do this intuitively, what we need is the following. So we need to construct a set of points, like you see over here, whose density goes to 0, but slower than the square root, and such that when we look at the difference set, the size of the difference set grows like the square. Okay, so under these two conditions, we could prove more formally that the Bernoulli density of the difference goes to infinity, and therefore that we could estimate the covariance. Okay, so the gory details are in these blue boxes, but the images kind of give you the intuition of why this is true. Okay, so just to make this a little bit more concrete, so one example of a density that satisfies these conditions is this ternary set. So if you take a line and you repeatedly delete the middle third of the line, you get this ternary set. And it's easy to convince yourself that the data points at the end have a density going to 0, but you can show that this density satisfies the two conditions we saw before, and therefore the density of the difference goes to infinity. So you could presumably build hardware that samples in this form, and you could then recover the covariance from a density going to 0. Now, of course, if you try to use, so this is a good set. If you try to use uniform sampling, then you will fail because the difference set and the set itself have the same density. So if the density of the set goes to 0, then so does the difference. So that's not a good example. Okay, so you could come up with these examples that satisfy our general conditions. So that's the good news. Of course, in practice, it's not so clear that you actually want to implement this in hardware. So what we want to do next is look at the types of hardware that we already developed for sub-Nyquist sampling and seeing if for those particular cases we could in fact reduce the sampling rate. So I'm not going to go through all of the examples. Let me just give one very popular example, and that's what's called multi-coset sampling, which is a very popular sub-Nyquist or Nyquist type sampler. So the idea in multi-coset sampling is that you take your sampling points, you divide them into blocks of length n times the Nyquist period, and in each block of size n times the Nyquist period, you choose m points. Okay, so if you want to sample at the average Nyquist rate, then m has to be equal to n. Okay, if m is smaller than n, then you're at a sub-Nyquist regime. So again, if all we know about the signal is that it's band limited, then we need m equals to n. We need to choose n points in an interval of size n times the Nyquist period. But what we can show is that if we only want to estimate the covariance, then the number of points we need is square root of n. Okay, so we have a savings of the size of square root of n with respect to recovering the signal because all we want is to estimate the power spectrum. And we can also characterize what types of multi-coset sampling enable that. Essentially, we need the differences between each of the point locations to be different, and this is what's known in the literature as a Coulomb ruler. Okay, so if you use a Coulomb ruler for sampling, then you can achieve this square root reduction in the sampling rate. Okay, so this is for band-limited inputs. We could do the same thing for multiband inputs with unknown location. So again, we get a savings of a square root. So we know from sub-Nyquist sampling that if our signal has this structure, then to recover the signal, we need 2 epsilon n points, where epsilon is the relative band occupancy. And again, if all we want is to estimate the covariance, then we need a square root of that. Okay, so we always get the savings of square root with respect to if we were recovering the signal itself. Okay, so that was our first application where we could reduce the sampling rate because we're not estimating the signal itself, but rather just its power spectrum. Now I want to look at a very different example. So here we are interested in recovering the signal, but unfortunately we have distortion. Okay, so sampling theory traditionally ignores the quantization. So the Shannon-Nyquist theorem, for example, does not have quantization taken into account. We look at a signal that's continuous in time, and we convert it to a signal that's discrete in time but continuous in amplitude. Okay, whereas source coding or Shannon theory typically looks at the rest of the chain. So it looks at a signal that is quantized in time but continuous in amplitude and converts it to a signal that has a fixed number of bits. And then, of course, it looks at the distortion between the recovered output and the original input. So basically what we would like is to unify the two, is to look at the rate distortion of a continuous time input. Okay, so to make that a little bit more specific, in standard source coding, like we said, we look at an input that's discrete in time but continuous in amplitude. We assume that we have a fixed bit rate R. And we asked ourselves, what is the minimal distortion we could get between the recovered output and the input if we use an optimal encoder-decoder pair? And that gives us the rate distortion curve. For a given rate, we get the optimal distortion. Okay, assuming that we design an optimal encoder-decoder. Now, what we're interested in is the case where we have a continuous time input and a continuous time output. So our distortion now is defined in this continuous domain. And we also have sampling that's part of our process. So we have a fixed bit rate, but we also have a sampler that we could design. Okay? So the question is, if we optimize over all encoder-decoder pairs and over all sampling functions, what is the minimal distortion we can get? And once we know what that minimal distortion is, a very interesting question is, what is the sampling rate needed to achieve that minimal distortion? And is it, in fact, the Nyquist rate? Or maybe we could go lower than the Nyquist rate. Okay? So deriving these results is quite involved. I forgot to mention, very important, it was on the slide, but let me say it specifically, of course, that this is joint work with Andrea Goldsmith from Stanford and her student Alon Kipnis. So they are the information theory people behind this, which is very important because my knowledge in information theory is quite limited, but growing hopefully with time. So here's the basic result we can show. So for a fixed sampling rate, we could develop the rate distortion curve of these continuous time signals. And I'm not going to go through the derivations. They're quite involved and kind of irrelevant to the main point I want to point out in this talk. But the important thing is that the distortion actually has a very nice interpretation. So we could write it as a sum of two terms, where the first term is a minimum mean squared error term that basically takes into account the sampling rate, whereas the second term is kind of a water filling term that takes into account the bit rate, the quantization effect. Okay, so we have this nice additive term here. And what we could do is, once we have these rate distortion curves for a given sampling frequency, ask ourselves, what is the optimal sampling frequency we need to achieve the minimum rate distortion? And what we get is actually a very interesting result. So what we can show is that as long as the input is not fixed, the spectrum is not flat, as long as it has some variability, then we could sample always at rates lower than the Nyquist rate without losing anything. We'll get the same optimal distortion. Okay, so here, for example, these are just some particular cases. What we're plotting over here is the minimum sampling rate needed to achieve the optimal distortion as a function of the bit rate. Of course, when the bit rate goes to infinity, we'll be back to the Nyquist rate, because then there's no quantization. And what we're plotting here are several examples. So this is a flat input with a bandwidth of 1. And indeed, the minimal sampling frequency is exactly the Nyquist rate, is 1. Okay, now if we look at these blue and red pictures, these are pictures that have the same bandwidth but have variability in the power spectrum. And in these cases, the minimal sampling rate could actually be much lower. Now, what's interesting is that these results are general. They have nothing to do with the input being band limited, and therefore we could use them to analyze non-band limited inputs. Okay, so we could ask ourselves, given an arbitrary input having nothing to do with band limited, what is the sampling rate needed to achieve a given distortion, assuming that we have a fixed bit rate? And we get this general curve. So our results give us basically sampling rates for non-band limited inputs as well. And what you see is that the sampling rate is finite. Okay, it doesn't go to infinity, as we would expect if we were trying to recover the signal perfectly. Okay, so this is the second example where there's basically no loss in optimality in sub-Nyquist sampling, even though the signal is not assumed to have any particular structure. Okay, so let me move on now to the last application, which is kind of more engineering oriented, so a little bit less mathematical, but I think has some interesting implications. So we're going to focus particularly on ultrasound, although the results I'm showing are valid more generally. But ultrasound is a very nice application. So we could think of ultrasound very similar to radar, where basically we're sending a pulse through the ultrasonic probe, and what we're viewing are reflections of this probe, of this pulse, as it propagates through the tissue. Okay, so in an ideal setting, we would get a line something like this, this nice pulse stream model. Now, unfortunately, in practice, this is not what happens. So the ultrasound environment is very, very noisy. We get multiple reflections within the tissues. And therefore, from a single line, like I showed before, actually you get nothing. Okay, we'll see some lines later on. They're very, very noisy. And therefore, what's done in practice is that in this ultrasound probe, we actually have multiple channels. So typically something between 128 and 256 channels. And what we do is that we receive these signals in each one of these channels. But remember, there's a fixed geometry to this probe. So just from geometry, we know the time lag between the reception of the pulse in these individual signals, in these individual channels. And it's a nonlinear function because this is near field. Okay, so we don't have the standard linear thing we get in radar, for example, because it's far field. So we have this nonlinear function. And now if we could take all these individual signals and align them according to this nonlinear function, then we could sum them up, increase the SNR, and increase the resolution that we get. Okay, and this is the process that's known in signal processing as beamforming. So this is done in all ultrasound machines. The difficulty with beamforming is that it's very, very costly. Because first of all, it requires sampling at a very high rate. In fact, they sample at rates that are much higher than the Nyquist rate because they want to implement these time shifts, these nonlinear time shifts, on a very fine grid. So it requires high sampling rate and very high processing rate because you get all of this data and you have to beamform it to every point in the image. So it's a very costly operation, and this is one of the reasons that ultrasound machines are so huge. So our first motivation was to try and kind of decrease the size of the ultrasound machine by reducing some of the processing rates. But the question is, first of all, could we reduce analog sampling in each run of the elements? But then the second issue is, even if we could reduce the sampling rate, how are we going to do the beamforming? So we don't want to reduce the sampling rate and then interpolate back to the high grid. Okay, that would defeat the purpose because the processing here is a lot of the cost. So the question is, could we sample at a low rate, but then somehow do this nonlinear processing from the low rate samples? And what we'll see is that this could be done by a process called compressed beamforming that I'll explain in the next few slides. And what this will allow us to do, like I said, is reduce the size of the machine, enable 3D imaging, which is very, very important because the volumes there are very high. It will enable us to increase the frame rate, which is very important in cardiac imaging. And finally, I'll show you a short demo of a wireless ultrasound. Because the data rate is low, we could do this remotely. OK, so let's put the beamforming aside for a second. Suppose we had that clean pulse stream model, which we don't have, but suppose that we did, meaning suppose we were directly sampling the beamformed signal. Well, then we could use the nice finite rate of innovation theory that tells us that if we have a signal that consists of, let's say, L pulses, then we could sample it using 2 L Fourier coefficients. And in the lab, we've developed some concrete hardware that allows us, in a very hardware-efficient way, to kind of achieve this sub-Nyquist sampling. OK, so the details don't really matter. What's important is that we have a board that if we had a pulse stream model, it will actually directly give us those low-rate L Fourier coefficients that we need. OK? Now, unfortunately, though, like we said, each one of these individual signals, like you see over here, so this is real data coming out of the ultrasound, they do not have a pulse stream model. OK? They're very, very noisy. There's many reflections off axis, and therefore, they just look like junk. Okay? But after we sample them at a high rate, so typically between 20 and 50 megahertz, the GE ultrasound machine we have in our lab actually samples at 50 megahertz. So after we sample them at this high rate and do beamforming, we get this nice pulse stream model. Okay? But now we have a chicken and egg effect, right? We want to sample the signal so that we could do beamforming and get a nice pulse stream model. But our theory allows us to subsample only the pulse stream model. Okay? But we don't actually have access to it. So it's not clear how we could enable this reduced rate sampling on the individual signals that have no structure. But what I'm going to show you now is that actually we can do this, and we could do this using a very simple observation. Okay, so simple in the sense that at the end it's simple. The derivations are kind of hairy and ugly, and that's probably why no one ever bothered doing them before. But there's nothing deep about them. Okay, it's just grinding through algebra. So what we can show is that that nonlinear beamforming equation you've seen before can actually be written in the Fourier domain in linear form. So what we can show is that the Fourier coefficients of the beamformed signal are given by this convolution between the Fourier coefficients of each one of the individual elements and this kernel Q. Okay, now this kernel is very, very ugly, but it's fixed. It depends only on the geometry of the array. So this is something that you compute once, and it's basically put into a table. And what's important about this Q function is that it's very narrow in frequency. It decays very quickly. Now, this relationship is just algebra, so it has nothing to do with structure or compressed sensing or sub-Nyquist sampling. Okay, it's just algebra. But why does this help us? Because what this tells us now is something very important. So what this says is as follows. This guy already represents the beamformed signal. Now, the beamformed signal, we know we could recover from 2 L Fourier coefficients. So all we need to compute are 2 L Fourier coefficients of this guy. Now, what this equation tells us is that if we need 2 L Fourier coefficients of this guy, then we only need roughly 2 L coefficients of each one of these individual signals, because that Q is close to a delta. Okay, so in the ultrasound demo, you'll see we actually use 3 points. Okay, so it's 3 times 2L. Now notice, we're not assuming any structure on these guys. So basically, we're doing sub-Nyquist sampling on each one of these individual elements, but we're not assuming they have any structure. Okay, it's only because the beamformed signal has structure that enables low-rate sampling of these individual signals. Now, what's important is that this extends immediately. It's just uglier, but extends immediately to 3D. And this is what's going to enable 3D reduced rate ultrasound imaging. So these are some examples from a true ultrasound machine. And actually, in the interest of time, let me skip this and go directly to the demo, and I'll explain it as the movie is playing. So what you're going to see now is actually a true demo of an ultrasound machine in our lab. So we have an ultrasound machine of GE. And what we did is we just put in our sampling device into the ultrasound machine. And we invited, so Dr. Sahd that you see over here is a cardiologist, a very well-known cardiologist in Israel. And he came to our lab. What you're seeing now is actually one of the students. This is all approved, so it's OK. But one of the students, and this is the Nyquist rate version. So basically what we asked him to do is to use the machine on both Nyquist and sub-Nyquist version and to tell us if he saw any difference. So we don't have sound here. You could see the demo online with sound where he goes ahead and explains exactly what he's seeing, so I cannot for the life of me repeat it, even though I've seen this movie many times. But the important thing is that from his perspective, he was seeing the same thing, both in Nyquist and sub-Nyquist. So this is a sub-Nyquist version. All of this, of course, is being done in real time, so it's very, very fast. The computational cost is low. It's done at sub-Nyquist sampling. And soon you'll see kind of still images just to compare between them. But from a medical perspective, and we had several cardiologists look at this, from a medical perspective, to them, this looks exactly the same. This is reducing by a factor of 1/30. So it's quite a substantial reduction in sampling rate. Again, 1/30 in each one of the channels. So the overall reduction is quite huge. What you're going to see now is some volumetric imaging, so 3D imaging. This is much harder to interpret. You'll see the images. They're much harder to interpret. This is phantom cardiac data. We don't have a true cardiac machine in our lab, and that's because they cost hundreds of thousands of dollars in 3D. They're still very expensive, and the resolution is still quite low. But here again, we could do sub-Nyquist sampling in 3D. This is the wireless demo that I was talking about. So because the rate is so low, what we do is we take the image at one side of the room, and this is just a demo in our lab, so we're sending it to the other side of the room over a very, very standard Wi-Fi link, so just the cheapest Wi-Fi link you could buy. Of course, in practice, you would imagine doing this over a server, over the cloud, or in a remote location, et cetera. But this proves the concept, and we get the same image. This is what's called a cardiac phantom, and this was important to GE because they used phantoms to make sure that we didn't harm the resolution. So that's why we're showing the phantom. Of course, we could do the same thing with real cardiac data. OK, so I was focusing on ultrasound. The same thing exactly is valid in radar. So the same, I won't go through the details here. The same ideas we use for ultrasound we could use for radar in order to get sub-Nyquist radar. Again, with the same advantages. So very good SNR, very good clutter rejection. We could take, because we could do the beamforming at these low rates, we could reject clutter and reduce and increase SNR. So I think, do I have another minute to show the? OK, great. So let me just briefly show the radar demo. Again, I'm not going through the theory for this. It's essentially the same as ultrasound. It's actually easier because the volume of data is much lower. So this is the actual board. This is the NI environment that simulates the radar environment. What you're going to see now is the input radar signal that has targets, clutter, and noise. So this is the input radar signal. It looks like the stream of pulses. This is the clutter that's added to it. This is the noise. And now when you see the combined version, you'll see that the signal is totally buried in the clutter and noise. So standard compressed sensing would have difficulty with these types of signals. But because we could do the beamforming at these low rates, we're able to get very good detection of the radar target. So here you see the delayed Doppler maps. And you see that we get very good resolution. We could reject the clutter. And this could work even if the targets are very close to each other. So you'll see that in the next example. We have targets that are very close to each other, and we could still distinguish them. This works even at very low SNR, again, because of this beamforming that's done on the sub-Nyquist samples. OK, so with that, let me wrap up. So what we tried to show today is that there's a variety of different cases where we could do sub-Nyquist sampling even though the input does not have structure. And there's different examples that we looked at. So in some of the examples, we were not interested in recovering the signal itself, but rather only a function of the signal. We also looked at examples, for example, when there was a distortion introduced to the signal anyway, like in quantization. And again, that enabled sub-Nyquist sampling. So these are, of course, just examples. Hopefully, this will inspire other work along these lines. But I think the important take-home message is that very often it's beneficial to take the processing task into account already in the sampling stage. Okay, so traditionally, sampling devices were designed kind of independent of the processing task. So you buy kind of your sampler, it's off the shelf, but then of course the DSP is very focused on the specific task. Basically what we're promoting here, and this is true both when there's structure and when there isn't structure, is that since the DSP is dedicated, you might as well make the sampling dedicated as well. And if you know your processing task, like in ultrasound, you could benefit a lot from rate reduction already in the sampling stage as well. So if you want more details on the hardware, you could take a look at our lab website. And thank you very much for your attention. Everybody wants to go have coffee. So.
Wow. Let me ask you. So I'm very curious in the beamforming about this spectral decomposition. I'm
Yeah, you could ask. I'm just going back.
You're getting a narrowband filter from this convolution, so you're separating things well already. Is that the right way?
So, okay, this just turns out by chance. It's like a lucky coincidence, okay, that this Q function, so this is just algebraically equivalent to that nonlinear equation we saw in time. Okay, so if you go back, let me just go back. Was it here? Yeah. So this equation in time, if you go through enough pages of algebra, it actually turns out to be completely equivalent to this equation over here. Okay, so that's just a mathematical relationship. Now, it turns out, and this was lucky, that these Qs, if you plot them in frequency, they happen to be very narrow band. Okay, if they were wide band, then we wouldn't get a benefit. So what this means is that to compute each Fourier coefficient for a given Fourier frequency, I only need a very small number of Fourier frequencies of the input signal. And therefore, if altogether at the output I need a small number of Fourier coefficients, it means I need a small number of Fourier coefficients of each of the individual signals. Okay, now if this Q would be wideband, it would still give us an advantage, but it's a subtle advantage. So the advantage is that now, because people sample in time, actually they sample at larger than the Nyquist rate. Because when you think about it in time, you think if I need small shifts, I need to be on a very, very fine grid. Okay, now if you would do it in frequency, even if this is very wideband, okay, you would still say, because you would only need a number of frequency that fit the bandwidth of your pulse. So your savings would be the ratio between the oversampling rate that they do today and the Nyquist rate. Here we get an even further reduction because Q is narrow, and we're able to go down to the sub-Nyquist rate because these guys represent a structured signal. Did that help clarify? Okay, we could talk more.